In this section, we're going to introduce the binomial theorem.
Let's begin with a simpler concept that we're going to need. Let's say I had 4 objects. All right, here I have 4 different dice. This one has 20 sides. This one's made up of 10 sides. That's got 6 sides, and this is a 4-sided die. All right, so let's say I were told, okay, here are 4 dice. You can choose any one you want. You can keep it. Well, then there's 4 choices, right? I have 1, I could choose this one, I could choose this one, or I could choose this one. There's 2 choices I can make. But now let's say I was told, okay, you know what? You can choose 2 of them. Any 2 you like. Well, I could choose these 2. Okay, so that's 1 choice I can make. Or here's another choice. Or here's a 3rd choice. Or here's a 4th choice. Here's a 5th choice. And there's a 6th choice that I can make. So given 4 objects, if I'm told choose one of them, well, I can make, there's 4 choices I can make. However, given those same 4 objects and I'm told to choose 2 of them, well, there's 6 different choices I can make. Now, what if I'm told to choose 3 of them? Well, I could choose these 3, or these 3, or these 3, or these 3. Well, notice that that's the same as saying choose 1. And you say, no, that's going to be different, right? Because I'm going to choose 3 instead of 1. Well, yes, but to say you're going to choose 3 to keep, that's the same as saying choose 1 not to keep. Oh, I choose this one not to keep. I'll keep these 3. Or I'll choose these 3 to keep, not that one. So here, if I'm saying choose 3 of them for you to keep, that's the same as saying choose 1 that you're not going to keep. So choosing 1 out of these 4 and choosing 3 out of these 4 is exactly the same kind of choice, right? The outcome of what you get to keep is different, but the number of choices you can make is exactly the same. I want to keep this one. 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 That's 4 choices. Oh, I don't want to keep this one. I don't want to keep this one. I don't want to keep this one, or I don't want to keep this one. That's still 4 choices. Right? So given a number of objects, how many choices can you make? So there's a notation for that. So NR, like this. Avoid the temptation to draw a line there. This is not a fraction. Here this is N and R. There's no bar here. There's no fraction. And here those are placed inside of parentheses. This kind of notation has actually a few different names. It can be called a combination. It can be called, or rather it can be called the number of combinations. However, the name that we're going to use here, and that's because it's most relevant to what we're talking about in this section, this is often called the binomial coefficient. And there are other names which you can go by, but for now we're going to call this the binomial coefficient. And the binomial coefficient can be thought of as, well, there's going to be a formula here in a moment, but what it can be thought of as is, okay, how many objects do you have? That's your N. Total objects. Your R is how many you're going to choose. Like that. So in our example of the dice, I have 4 dice, and I'm going to choose 2 of them. All right. Oh, it turns out I had 6 different ways to do that, which we counted earlier. Oh, that would be read as 4 over 2. Again, that's not a fraction. The way you would read this is 4 choose 2. So the notation would be 4 over 2. Again, avoid the temptation. This is not a fraction. Don't write a bar here. Put that in parentheses. And this is equal to 6. Because if you have 4 dice, or 4 of anything, and you want to choose 2 out of those 4, there's 6 different ways you can make that choice. And this is read as 4 choose 2. There you go, 4 choose 2. That is read as 4 choose 2. Okay, so how do you find this? Well, obviously one way is you can actually grab 4 objects and choose 2 and count them up. But if the number was something like 12 choose 7, that might take you a while to count them all up. So instead, we have a way of evaluating the notation without grabbing physical objects. So here we're going to consider this a definition. We're going to begin with two non-zero integers. Here, n and r. Well, actually, not even integers. We're going to use only counting numbers, right? Let's see here. Well, we can't have these be 0 because you can choose 0 objects. That means just don't grab anything. Okay, so let's write it this way. Let r and n be whole numbers. Okay. So remember, your whole numbers, those are starting from 0 and going on up. Your whole numbers are 0, 1, 2, 3, no negatives, starting from 0 on up. Okay. Let r and n be whole numbers such that your n will be greater than or equal to your r. It's okay if you have 4, choose 4. You can't have 4, choose 5. You can't say I have 4 dice. Okay, well, I'm going to pick 5 of them. That doesn't work. The top number has to be greater than or equal to the one on the bottom. All right. Then n choose r is equal to n factorial over r factorial times n minus r factorial. Here, this can be shown with some material that's not entirely appropriate for our current course of study. This is something that comes from number theory. When you're, it's basically counting theory. I know it sounds like counting is an easy thing to do, and yet if I give you 400 objects and tell you to choose 76 of them, it would take you a very long time to count how many choices you can make. So there actually is such a thing as called counting theory, a way of efficiently counting very large numbers. So here we're not going to go through the details as to exactly why these are equal to each other. That's not quite appropriate for our current course of study. It's from a different field of math. So here we're going to largely take this for granted. We're going to say, yeah, this works. Just as a simple example of this, let me go ahead and show that that's true using this definition. If I have 4 objects and I'm going to choose 2 of them, that's going to equal to, all right, we're going to take the top number, factorial, 4 factorial, over, and now you're going to take the bottom number, factorial, and then you're going to take the difference in those two numbers, 4 minus 2 factorial. Okay. All right, well, 4 minus 2 is just the number 2, so you can write that as 2 factorial. But remember, 4 factorial is 4 times 3 times 2 times 1. 2 factorial is 2 times 1, and again, 2 factorial is 2 times 1. So here these 2's divide away. And here 4 over 2 is the same as 2 over 1. And so you're left with 2 times 3 in your numerator and 1 times 1 in your denominator. So 6 over 1, which is just 6. So here, this does match up with what we saw physically using our 4 dice. Okay? Here, 4 choose 2 is a common way of saying this. In other textbooks or in other vernacular, some people will also say 4 over 2, or some people will even say 4 above 2. All of these are interchangeable. It's just a manner of speaking. 4 choose 2, 4 over 2, or 4 above 2. Just because of my background, where I studied this and where this is relevant to me, I almost always use this first language, 4 choose 2. However, if you use any of the other ones, those are also correct. They're interchangeable. So go ahead and give this a try. If you had, let's say, 6 objects, let's say I had 6 dice now, and I told you to choose any 2 of those 6 dice, how many choices would you have? Go ahead and pause the video, give that a try, and once you're done, go ahead and unpause, and we go through that together. Use this definition. Don't go grab 6 dice, unless you really want to. All right, so here we go. 6, that's your n. So that's going to be 6 factorial over. You're going to take your r, and that's going to be factorial in the denominator. And then the difference of those, factorial, also in the denominator. Okay. Well, 6 minus 2, that's going to be 4. So that's going to be 6 factorial over 2 factorial, 4 factorial. And remember, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. And 4 factorial is 4 times 3 times 2 times 1. Oh, notice these 4 divide into those 4. Right? 1 over 1, 2 over 2, 3 over 3, 4 over 4. Those are all the number 1. Here, notice 6 over 2 can be reduced to 3 over 1. And that looks like that's it. So your numerator is 3 times 5. Your denominator is now the number 1. Oh, 15 over 1. 15. So if I give you 6 dice and tell you can choose any 2 of these, there's 15 different ways you can choose a pair of dice. There is one that almost seems like it doesn't make sense until you remember the definition of 0 factorial. And that's if I have 6 dice and I tell you to not choose any. 6 choose 0. That sounds like that nonsense, right? Except if you think about it, it becomes pretty apparent what it is. Let's say I have 6 objects. So I have my my dice from before. Here are 4 objects. I need 2 more. There we go. That's a 8-sided die and a, what is this, 10-sided die, I believe? Yes, I believe. A 12-sided die. There we go. So we have, whatever. We have 6 different dice. And I tell you, okay, here are 6 different dice. You're not allowed to take any of them. How many ways can you do that? Well, there's only one way to do that, and that's by saying, okay, well, those are nice dice. I guess I'm walking away now. The only way to take 0 dice is to take 0 dice, is to leave all 6 of them there. There's only one way to do that. Here, we can actually confirm that from this definition. That's going to be 6 factorial over 0 factorial over 6 minus 0 factorial. That number, the difference of those numbers. 6 factorial. Remember, 0 factorial by definition, so here I'll say recall, 0 factorial is equal to 1. So that's the number 1. Times 6 minus 0 is still 6. And here these numbers divide away. A number divided into itself is the number 1. So sure enough, even by this definition, it matches what we would think of from a physical example. You have 6 different dice, and I tell you you're allowed to take absolutely none of them. Well, there's only one way to do that, and that's by saying, okay, well, I guess I'm not taking any of them. Say goodbye to them, and that's it. Huh? Now, if you look at the binomial, I never actually labeled that, did I? I labeled it up here, but I should label that in my definitions as well. So then this equals this is called a binomial coefficient. Okay. All right. So when we're talking about binomial coefficients, these things right here, there does arise an interesting pattern. Okay. So let's say we have a few of these that we're going to find. Let's begin with having n equal to 0. All right. Now you might say, well, how does that happen? Well, just thinking about it from a physical standpoint, I have 0 dice here. Now I'm telling you, you can choose none of them. Okay, well, there's one way to do that, and that's by looking at you with a confused face and saying, okay, I guess I don't take anything, and then walk away. So here I'm going to write a few binomial coefficients. I'm going to have 0 choose 0. Okay. Now remember, the bottom number has to be less than or equal to the number on top. So that's it. That's the only one that I could put under here, because I can't put a 1 or a 2 here, because that would be greater. Okay, but now I can have 1 as n, and now there's 2 choices for r. Because again, r has to be less than or equal to this n. So I can either choose 0, which is less than 1, or I can choose 1, which is equal to 1. Okay, so that's the only choice of r that I have whenever n is equal to 0. I have 2 choices for r when n is equal to 1, because again, these have to be less than or equal to n. Okay, well now I can make that a little bit bigger. I can say 2, and if I have 2, I have, I have 3 choices. I have 2 choose 0, 2 choose 1, and 2 choose 2. Again, these are all the numbers that are less than 2. I can do 3 choose 0. I can do 3 choose 1, 3 choose 2, and 3 choose 3. Okay? And so forth and so on. Notice that at each level I have one more possibility than I had before. So here's what happens whenever n is equal to 0, when n is equal to 1, when n is equal to 2, when n is equal to 3, and so forth. If you compute these numbers, there turns out to be an interesting pattern to these. So 0 choose 0 is 1. Okay? And again, you can do that by just a physical example. There are no dice here. Choose none of them. Well, I do that by looking at you with a confused face and walking away. There's only one way to do that, right? Or if you prefer, you can use the formula here, 0 factorial over 0 factorial, 0 factorial. Well, since 0 factorial is always equal to 1, that's 0 over, that's 1 over 1 over 1, which is 1. 1 choose 0 is 1, and 1 choose 1 is 1. Again, the idea being I have a single dice right here, and from that single dice, I can tell you that choose none. Well, one way to do that is by not picking it up, and that's it. Or choose 1. Well, the only way to do that is by picking up that one dice, that one die. So that's it, 1 and 1. And of course, you can always compute these numbers. Note that on most scientific calculators, there is a button that will compute these numbers for you. Right here, at least on my calculator, it looks totally different than what it would look like if you were writing it. Here, you don't have like a parenthesis button. It won't look like this. It's this button right here on my calculator, at least. NCR. Here, C stands for choose. So N choose R. Not quite literally the same that we had over here. 4 choose 2. So the way you would write that is if I want to find 4 choose 2, I would say 4. And then I would hit my C button. And then 2 equals, and sure enough, it's the same 6 that we computed earlier. So here, if I want to compute what all those numbers are, I can go ahead and grab a calculator and churn those out. Here, 2 choose 0 is 1. 2 choose 1 is 2. And 2 choose 2 is 1. Here, 3 choose 0 is 1. 3 choose 1 is 3. 3 choose 2 is 3. And 3 choose 3 is 1. At this point, you say, well, wait a minute, I thought you said you were going to grab a calculator and churn those out. Well, you can. That is absolutely one way to do that. For example, right here, if I say 3 choose 2, that gives me the 3 that I had before. And you say, yeah, but you didn't grab a calculator. You just did that in your head. Are you just doing that in your head? Well, I could, I suppose. But what I'm doing is I'm taking advantage of a pattern. Whenever you have a set of binomial coefficients, let's say I want to find the next level. The next level, without having to write this, without having to do any of this, or without grabbing a calculator, I can tell you it's 1, 4, 6, 4, 1. That's 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, and 4 choose 4. At this point, you might be thinking, oh, you probably have these memorized. No, I don't have them memorized. You might find that an interesting challenge if you don't know about this pattern yet. Go ahead and pause the video and see if you can figure out what the pattern is. What do you think would be would be 5 choose 0, 5 choose 1? What do you think the next row would be? All right, so the pattern is this. Notice that on the outside you always have the number 1. Because if you have 1 object or 2 objects or 3 objects or any number of objects, and I tell you, hey, here are some objects, choose 0 of them, well, then you just don't pick anything up. There's only one way to do that. On the other side, you have, for example, 3 choose 3. I have 3 objects, and I'm telling you to pick 3 of them up. Well, there's only one way to do that as well, and that's to pick them all up. So the number on the ends is always going to be the number 1. You say, okay, great. So the numbers on the ends are always going to be the number 1. But what about the rest? How are you doing the other one so quickly? The pattern is this. If you take a look at the adjacent sides and add them together, that gives you this number. So 1 plus 1 is 2 right here. 1 plus 2 is 3. 2 plus 1 is 3. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. If you take the two numbers right above it, add them together, that gives you the number below. So here, the next numbers would be 1 plus 4, that makes 5. The next one would be 4 plus 6, that makes 10. 6 plus 4, that also makes 10. And 4 and 1, that makes 5 when you add them together. So these are the binomial coefficients for 5. So this is 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, and 5 choose 5. The next one, if I had 6, 6 choose 0, 6 choose 1, 6 choose 2, 6 choose 3, 6 choose 4, 6 choose 5, and 6 choose 6. The ones on the outside are always 1. This right here has a name, this pattern. There are a few different people who've discovered it throughout history. The one with the best publicist, I guess, the one with the best PR was Blaise Pascal, a French mathematician. So in many books, this is called Pascal's triangle. However, Pascal was not by no means the first person to discover this in any way, shape, or form. Pascal first stumbled upon this. Now, to be fair, he wasn't stealing it from anyone. He did independently discover it, but he found it in the 1600s. This has been, we have found copies of this in Chinese manuscripts going back over 1,000 years. We have found these in manuscripts in different countries because the applications of this show up in lots of different places. They show up whenever you're doing any kind of algebra, and they show up whenever you're distributing goods. It has to do with, hey, I have a certain number of people and I have to distribute a certain number of things. How many choices can I give them? Yeah? So these kinds of things show up in many fields of math. And again, Pascal probably just had the best publicist. So in most books, it's called Pascal's triangle. But again, Pascal only discovered it in the 1600s. We've historically as the human race, we've had this pattern for over 1,000 years. Okay, so why are we bringing it up now? And what does it have to do with binomials? You're calling it a binomial coefficient. Isn't coefficient usually the number in front of an x? Like 2x squared, isn't the 2 called a coefficient? And what do binomials have to do with it? Well, what happens if you take x plus 1 and you square it? Oh, well, that's easy. I can get, x plus 1 times x plus 1. I distribute and combine like terms, and I get x squared plus 2x plus 1. Okay, well, what happens when I take x plus 1 and I cube it? Well, that's, I take this thing right here, which is already x plus 1 squared, and I multiply it again by x plus 1. So that's going to be x to the third plus 3x squared plus 3x plus 1. And if you doubt that, you can actually do that. Just do the multiplication. It'll give you that result. Hey, look. 1x, 1. 1 and 1. 1x squared plus 2x plus 1. 1x cubed plus 3x squared plus 3x plus 1. Hey, you know what? I bet you without having to multiply anything out, just off the top of my head, I can almost guarantee, or in fact, I can guarantee, that this is going to be x to the fourth plus 4x to the third plus 6x squared plus 4x plus 1. And if you doubt that, go ahead and multiply that out 4 times, and I guarantee it'll give you this, 1, 4, 6, 4, 1. Because among other things that the coefficients of this triangle represent, among other things that the numbers in this triangle represent, they represent the coefficients of expanding the binomial x plus 1. X plus 1 to the second power, hey, just use n equals 2. Those are your coefficients. To the third power, oh, use n equals 3, and that's your coefficients. Fourth power, oh, when n is equal to 4, those are your coefficients. At this point, you might say, okay, well, that's nice, I guess, but isn't that really, really limited? Because how often do I need to square x plus 1, or cube x plus 1, or take x plus 1 to the 4th or 5th or 6th power? Yeah, I guess it's a nice shortcut for specifically that example, but that seems really rather limited. Well, it turns out that with just some slight modifications, we can use these coefficients to expand any binomial. So let's take a look at that. All right, so let's say we're going to expand a binomial. Well, the nice thing about binomials is they all look exactly the same. You have something, which I'll represent with an A, plus something else, which I'll represent with a B. And you might say, well, wait a minute, isn't it also sometimes A minus B? Well, sure, but you can make B a negative, can't you? After all, we're not saying what A or B are at all. So if you want a minus here, you could always just make that one into a negative. So here, all binomials are basically something plus something. And maybe one of those somethings is a negative, but it's still something plus something. All right, so if I raise it to the first power, well, raising something to the first power just leaves it alone. Okay, so that's going to be a plus b. Okay, what if I raise it to the second power? A plus b squared. All right, well, let me go ahead and do that down here. A plus b times a plus b, that's a squared, plus ab, plus another ab, plus b squared, which gives us a squared plus, that's two of those, so 2ab plus b squared. So that's a squared plus 2ab plus b squared. Okay. Now, what if I take a plus b to the third power? Okay, well, I already have a plus b squared, so let me take that answer and just multiply it by another a plus b. Okay, so a plus b times, again, this is already a plus b squared, so if I just multiply it by another a plus b, that'll be a plus b to the third. Oops. All right, so a times a squared, that's a to the third. That's going to be 2a squared b. And that's ab squared. And then this way, I have a squared b. And then I have 2ab squared. And then that's b to the third power. B times b squared is b to the third power. And we can combine like terms. Notice this one and this one are like each other. And this one and this one are like each other. So this will give us a to the third. When you combine those two, that's going to give you 2a squared b. Oh, sorry, plus 1a squared b. That's 3a squared b. Plus, when you combine those two, that's going to be 2 plus 1. That's also 3ab squared. 3ab squared. And then the last one is going to be your b to the third. Like that. Okay? And let's do one more. Let's say a plus b to the power 4. Well, again, that's we already have a plus b to the power 3. That's this one. A to the power 3 plus 3a squared b plus 3ab squared plus b to the third. And, oh, like I said, let me put this one in front. And I'm going to multiply that a plus b to the third times another ab to give me a b to the fourth. So that would be a to the fourth. That would be plus 3a cubed b. That would be plus 3a squared b squared. And that would be plus a b cubed. Plus, let me do this one. That would be a cubed b. That would be 3a squared b squared. Notice those line up. And then that next one would be 3ab to the third. And finally the last one, b to the third times another b would be b to the fourth. So here that's going to be 1a to the fourth plus 3 plus 1 is 4. A cubed b plus 3 and 3, that makes 6 a squared b squared plus 3 and 1, that makes 4 ab cubed. And finally, the b to the fourth is on its own. Oops, b to the fourth. Okay. Notice the pattern. 4, 3, 2, 1, nothing. The power of a starts from the maximum power of 4 and then goes down 3, 2, 1, nothing. Meanwhile, the power of b starts with nothing at all. There's no b here. And then power 1, 2, 3, and 4. That happens for all of them. That's got a maximum power of 3, so the a starts with 3, 2, 1, nothing. And the b starts from the bottom, nothing, 1, 2, 3. Here, that a starts with the maximum power of 2, 2 and 1, and 0. And the b starts with power 0, then 1 and 2. And notice the coefficients, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Those are the binomial coefficients that we see in our triangle over here. So that leads us to the following theorem. This is called the binomial theorem, or sometimes called the binomial expansion theorem, depending on what book you're looking at. Theorem. The binomial theorem states that for any positive integer, for any I guess let's say counting number, for any counting number n, now 1, 2, 3, 4, 5. If you take a plus b, and it doesn't matter what a and b are, they can be positive, negative, doesn't make a difference, and raise that to the power of n, you're going to have n choose 0 times a to the maximum power, which is n, and then b to the minimum power of 0. You can write b to the 0, or you just don't write b there at all. Either one's fine. Plus, you're going to have n choose 1. Your powers of a are going to get smaller one at a time. So the first one will be n minus 1, and then your powers of b will increase one at a time. So that's going to be b to the power 0. Okay, so there was no b. Over here, we're going to have b to the power 1 plus n choose 2. Again, you're going to decrease this power of a by another 1. So that's now a to the n minus 2. And you're going to increase the power of b by 1 more. So now that's b to the power 2. So n choose 0, n choose 1, n choose 2, n choose 3, and so forth. Notice that this bottom number matches the power of b. No b. Power 1, power 2, the next one will be power 3, 4, 5, and so forth. Also note that your power of a matches this one at first and then slowly decreases as you go forward. This keeps on going and going, but of course this does eventually end. There is eventually a final term to your binomial, and that last one's going to be n choose n, which again we've seen is the number 1 over here. We've always seen that the numbers on the beginning and the end are always 1. So it's going to be n choose n. By this point, your a has completely lost all power, so it's a to the 0, which you might also just not write an a, and your b is now at full power, b to the power n. This is also can be written in summation notation. This is the sum as r goes from 0 to n of n choose r, a to the power n minus r, b to the power r, where again you start with r equals 0, and then 1, 2, 3, 4, 5, all the way until you reach n. And either of these is acceptable to write. This is our binomial expansion theorem, or just the binomial theorem, depending on where you're looking. All right. The proof of this can be done by induction. So let's take a look at a proof by induction. Okay, remember that by proof by induction you have 2 steps. Step number 1, you're going to confirm the truth of case 1. Confirm case number 1, S1. Okay, well, let's see. In the case of S1, all you would have is a plus b to the first power. And here that would be 1 and 1, right? So let's see. That would be a plus b to the first power, and that's equal to 1 choose 0, a to the first, 1 choose 0, a to the first, and then there's no b for that one, plus 1 choose 1, that's not a fraction, that's binomial coefficient, 1 choose 1, n to the, okay, well this is the number 1 right here, so 1 minus 1 is 0. Okay, so I can write 1 to the 0, I just don't write anything, times my b. Oh, but 1 choose 0 is 1. A to the first, and 1 choose 1 is also 1, b. In other words, it's equal to a plus b, which, sure enough, is true. Okay, so this binomial expansion theorem is confirmed for the case where n is equal to 1. Okay, now, the next step is to confirm that if it's true for s sub k, if it's true for some arbitrary k case, then it must be true for k plus 1. All right? So here I'm going to take what I sometimes refer to as step 1.5. It's not technically a step in induction. However, it is useful to have an idea as to what your answer should look like if the proof is valid. So here, what will the result be for case k plus 1, I guess I should say s of k plus 1, sub k plus 1, if the theorem is true. So this is basically wishful thinking. If everything works out, what should this look like? Well, let's see. We should have a plus b to the power k plus 1. And that should look like, well, here I'm just replacing all of my n's with k plus 1s. Okay, so that's going to be k plus 1 choose 0, a to the power k plus 1, plus k plus 1 choose 1, a to the power, and again, you're reducing this by 1, so that would just be k, and that would be b, plus k plus 1 choose 2, and again, you're subtracting 1 from this, so that's going to be k minus 1, and you're increasing the power of b by 1, so that's b to the second, plus dot, 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 and eventually, over here, this will be k plus 1 choose k plus 1, instead of n choose n, it's k plus 1 choose k plus 1, b to the power k plus 1. Right? So that's what we should get if everything works out nicely. Okay, so let's see what we do get. So step 2. Assume the truth of case s sub k. All right, so let's say we know that this theorem is valid for some case, which we do. We know it's true for at least case number 1, right? So that would look like this. It would be a plus b to the power k is equal to k choose 0, a to the power k, plus k choose 1, a to the power k minus 1, b, plus k choose 2, a to the power k minus 2, times b squared, plus dot, 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 all the way down to k choose k, b to the k. And what I wish to do now is I wish to find out what happens when I try to turn this into case s sub k plus 1. Okay, well on this side that's easy enough to do. I just multiply by another a plus b. Basically I've confirmed this is true for k, for the power of k. So now if I want to go to the power of k plus 1, I just need to multiply it by a plus b one more time. All right, here if I multiply this times itself, that power goes up by 1 more. Okay, well whatever I do to one side of an equation, I do to the other side. So that's also a plus b right there. Okay, so now I need to start distributing. First of all, let me distribute the a. So all of these are going to get multiplied by a. So that's going to be k choose 0. And now this a to the power k, well, you multiply by another k. So that's now k to the power, a to the power k plus 1. Plus k choose 1. And that's going to be a to the power k. Because again, you're multiplying by a, so the power of this one goes up by 1, from k minus 1 up to k. And the b is not affected yet. Plus k choose 2, and again, this one goes up by power of 1, so now that's a to the power k minus 1, b squared, plus dot, dot, dot. And eventually you're going to get down to here, where this last one's just going to get an a. Didn't have one before, it's going to get one now. So it's going to be k choose k, a, b to the power k. Okay? So what I've done right now is I've distributed my a's. But now I have to distribute my b's. Okay, so plus, notice that when I distribute my b's, this a, k will be multiplied by a b, AKB. Oh, it'll be a like term to this one. So I'm going to put it right under here so that it lines up, so that I have an easier time adding. So when I multiply this first term by a b, I'll get k choose 0, a to the power k times b, plus k choose 1, a to the power k minus 1, k choose 1, a to the power k minus 1, and then that b multiplies that b to give me a b squared, and these are like terms. And it looks like that's going to keep happening. Here, if I multiply by b, the term right before this one would be k minus, oh sorry, that would be k over k minus 1, k choose k minus 1, and that would be a b to the power k. And finally, if I multiply this very last one by a b, that's just going to raise the power by 1. There's no more a on this last one, so that's going to be k choose k b to the power k plus 1. So there's no a on that one. I've distributed a b, so there's no a on this one. There's only a b to the k times another b is b to the k plus 1. Okay. All right, so now we can add those. Okay, well, this one's going to stay the way it is. And this is going to stay the way it is because there's no like terms to these. This is a to the power k plus 1. Nothing else has that. And this is b to the power k plus 1, and nothing else has that. So they're going to stay the way they are. But now these need to add, and these need to add, and these need to add. Okay, well, how do you do that? How do you add when you have k choose something and k choose something else? How do you add those? Well, it's not just k choose something and k choose something else. Notice that whatever this one is, this bottom number is always one bigger. 0, 1, 1, 2, k minus 1, k. So what I need to do, and I'm going to go ahead and do this off to the side, let's say side work right here. Side work. I need to figure out what that is. What is k choose, let me call it k choose, oh, I've fallen into my own trap of making that a fraction. It happens to everyone, or at least it happens to me all the time. K choose r, and I'm going to add k choose r plus 1. I need to know what happens there, because that's what all of these are. This is k choose a number plus k choose a number bigger. K choose a number plus k choose a number that's bigger. So k choose a number plus k choose a number that's bigger. Okay, so I need to figure out what that is. All right, well, let's do that. We have definitions for these. This is going to be k factorial over r factorial times, let's see here, times k minus r factorial plus, and this is going to be k factorial over r plus 1 factorial times k minus r plus 1 factorial. All right, so that minus that factorial. Okay, well, in order to add these, they need a common denominator. Okay, well, that's r factorial and that's r plus 1 factorial. So if I multiply this by r plus 1 on the top and bottom, r factorial times r plus 1 is r plus 1 factorial. So now these are the same. Over here, notice that this one is bigger than this one, because here you're subtracting r plus 1. Here you're subtracting r. So here you're subtracting more. Since you're subtracting more, this whole thing is smaller. Okay, so we need to get this one up to the size of this one. Oh, well, it's only smaller by 1, because you only subtracted an extra 1. Okay, so you just need to multiply by that last term, and now these are the same. So here I'm going to multiply this by k minus r. So if I multiply this by k minus r, this k minus r plus 1 factorial times k minus r, that's k minus r factorial. And again, whatever I do on the bottom, I do on top. Okay, so that's going to be what? Well, let's see, I can put these together under a common denominator now. After all, these multiply together to be the same as that. So the common denominator will have an r plus 1 factorial. And these two multiply together to give me this. So this denominator will have a k minus r factorial. Okay, and then here I can distribute this. So that's r times k factorial. So let me just write that r times k factorial plus 1 times k factorial. That's just k factorial. Plus k times k factorial. and then that's got a minus on there, so it's minus r times k factorial. Notice those two cancel out. And so what are we left with? Well, let's see. We're left with, well, notice those have a k factorial. It's a common factor. Okay, so that's k factorial. And then once I factor out the k factorial, that leaves me a 1 because I factored out the whole thing. And here if I factor out the k factorial, I'm left with a k. So when I factor out k factorial, I'm left with k plus 1 over r plus 1 factorial, k minus r factorial. But notice, if I take k factorial and multiply by k plus 1, that's k plus 1 factorial over r plus 1 factorial. And that's k minus r factorial. But by definition, that's k plus 1 choose r plus 1. Notice that's the same formula. That k just became a k plus 1. That r became an r plus 1. And then here, since they both have a 1, when you subtract, the 1 cancels, and you're still left with k minus r factorial. So here, this is nothing more than k plus 1 instead of my k, and r plus 1 instead of my r. So this will equal to k plus 1 choose r plus 1. Okay, so over here, let's see what that is. That's going to give me k choose 0, a to the power k plus 1, plus, if I add these two together, what will happen is I will have to increase the power of the top number by 1, and I will choose the bigger of the two bottom numbers. Okay, so increase that k by 1, make that k plus 1, and then choose the bigger of the two bottom numbers. So that's going to be k plus 1, choose 1. And then here, these are like terms, so you're just going to leave that as a, k, b. Same thing here, you're going to increase this by a power of 1. So that's going to be k, not by a power of 1, just by 1. So k plus 1, choose, and then choose the bigger of those two, right? Choose the bigger of those two to be your bottom number. So that's going to be, the bigger of those two is 2. A sub k minus 1 b squared plus dot dot dot. Here, that's going to be k plus 1 is my top number. And then I'm going to choose the bigger of those two. Okay, well, I'm going to choose k. And that's going to be a, b, k, plus, and then this one, well, nothing happens to this one. It just stays the way it is because it didn't have any like terms to combine with. I did it again. There we go, k. B to the k plus 1. Well, notice that's almost exactly what I want. That matches that one. K plus 1 choose 1, a to the k b, plus k plus 1 choose 2, a to the k minus 1 b squared, plus dot dot dot. The only things that aren't matching are the first one and the last one. That one and that one. Those don't seem to match. Oh, but it doesn't matter. You say, why doesn't it matter? I mean, they're not the same, so that means you didn't get what you wanted. Remember that when you choose 0, you always get 1. Notice over here, 2 choose 0 is 1. 3 choose 0 is 1. 4 choose 0 is 1, always. Oh, so right here, k choose 0 is the number 1. So if I had a different number here besides k, it would still be 1. So you know what? Why don't I just call that k plus 1 choose 0? It's going to give me the same result. K choose 0 is 1. K plus 1 choose 0 is also 1. So here, I don't need to have this be any specific number. I can change it to whatever I want. So why wouldn't I change it to be the one I need? Same thing with the last one. Notice that k choose k is also always 1. 1 choose 1 is 1. 2 choose 2 is 1. 3 choose 3 is 1. 4 choose 4 is 1. K choose k is always 1. So here, as long as these are the same, I have the number 1. So you know what? Why don't I just make them both k plus 1? After all, k choose k was 1. K plus 1 choose k plus 1 is 1. Since they're both 1, well, it doesn't matter which one I use. So let me use the one that I needed. But there we go. If I have the truth of s sub k, then by multiplying by a plus b, this now confirms that it's true for s sub k plus 1. Thus, the truth of the case s sub k implies the truth of s sub k plus 1. Oh, but we know that it works for the first case, which means that now that implies it must work for the second case. Oh, but that in turn implies that it works for the third case, and the fourth, and the fifth, and the sixth, and it works for every possible case for any whole number. So, by induction, that concludes our proof. Therefore, by induction, that concludes our proof. And that makes us happy. So let's take a look at some examples now of using this proof. Right? We've talked about the notation, we've given the statement of the theorem, and now we've proven it. So once you prove a theorem, you're free to use it for application. All right, so example, go ahead and expand. Let's go ahead and expand 2x plus 3y to the power 5. All right, so by our theorem, that's going to be 5 choose 0. You're going to take the first term and start with it at full power, so that'll be 2x to the power 5. And then your second term, you won't have it appear in the first term at all. Or you can write 3y to the power 0, which again is just the number 1. So most people just don't write it. If you want to write it to the power 0, you may. The next one will be 5 choose 1, and that will be 2x. Okay, so now the first term will slowly start to lose power, and the second term will slowly start to gain power. So that'll be 2x to the power 4 times 3y to the power 1, plus 5 choose 2, and that will be 2x to the power 3, 3y to the power 2, plus 5 choose 3, 2x to the power 2, 3y to the power 3. Notice this bottom number always matches that one. Also note that the sum of those two is always equal to that one, right? 2 plus 3 is 5, 1 plus 4 is 5. These two powers always add up to the top one. The second power always matches the bottom one. Let's see, plus 4 choose 4, 2x to the first power, 3y to the fourth power. And finally, 5 choose 5, and I know I'm done because you can't have the bottom number ever be bigger than the top one, so you stop at 5 choose 5. The last one, you can write 2x to the power 0, but most people just don't bother writing it since it's completely lost power. And now this one will have full power, 3y to the power 5. Okay. All right, so let's see. We know what these numbers are, the binomial coefficients along 5. You can grab a calculator and do that. You can compute that using the formula that involves the factorial, or you can use this triangle. And either way, you get the same numbers. The binomial coefficient for the power of 5 are 1, 5, 10, 10, 5, 1. So this is 1, 5, 10, 10, 5, and 1. So now we simplify. Here we go. 2 to the 5th power, that's 32. X to the 5th power times 1. Okay, so the first term is 32 x to the 5th power. Plus 2 to the 4th power, that's 16. 16 times 5, that's 80. Times your 3, that's 240. And then your x has a 4th power and your y has a 1st power. You see how that's working? 2 to the 4th is 16. So you're just multiplying your numbers. 16 times 5 is 80, times 3 is 240. X to the 4th and y to the 1st. Don't really just worry about the numbers and the variables, just keep those powers. The next one, let's see here. 3 squared is 9. 2 to the 3rd is 8. 8 times 9, that's 72. Times 10, that's 720. X to the 3rd, y squared. Just like that. Plus the next one, 3 to the 3rd, that's 27. 2 to the 4th, 2 to the 2nd, that's 4. And if you take 27 times 4, that's 108. Yeah, 108, and then times your 10 here. That's 1080. And then you have your x squared and your y to the 3rd. plus. Let's see here, 3 to the 4th, that's 81. 2 to the 1st, that's 2. So 2 times 5 is 10. And 10 times 81, that's 810. X to the power 1, y to the power 4. And finally here, 3 to the 5th power, that's 243. Yes? 243 times 1 is still 243. 243. And then you have y to the 5th power. And there we go. That's 2x plus 3 raised to the power 5. This will work for any binomial raised to any counting number as its power. So the sum of two terms. If you have the difference of two terms, just keep the negative as part of this one. If this was, for example, 2x minus 3y, you would just think of that as 2x plus negative 3y. And the negative would follow the 3 throughout the problem. All right? Go ahead and give this a try. Go ahead and expand. Oh, I don't know. Let's go with 4x minus y raised to the power 4. Go ahead and give that a try. Pause the video. Give yourself the time you need. Note right here that you can write this as plus a negative y. So the negative will be part of the y. That'll be part of that term. All right? Once you're done, go ahead and unpause the video and we'll go through it together. All right, so that's going to equal to, that's 4 choose 0, and we know that because of this power. Over here we're using 5 because of the power 5. Now we're using 4 because of the power 4. 4 choose 0 times 4x to the full power of 4, and then your negative y has no power here, so you just don't write it. Plus 4 choose 1, that's 4x. This will slowly start to lose power, so now we have power 3. And your negative y will start to gain power, so that's power 1. Plus 4 choose 2, not a fraction, there we go. 4 choose 2 times 4x to the power 2. Again, we're slowly losing power, 4, 3, 2. And then your negative y will now have a second power, power 0, power 1, power 2. Again, the power of the second term always matches the bottom number. Next one will be 4 choose 3. Times 4x to the power 1, or you can just say 4x. And this negative y now has a power 3. And finally, we have 4 choose 4. This one has now completely lost power, so it's just 1. Right? So we don't need to write it. And now you have your negative y to the 4th power. Like that. So now we simplify. You can either grab a calculator and find those coefficients. You can use the formula that involves a factorial, or if you remember the triangle. Either way, you're going to get the exact same coefficients. When you're using a power of 4, your coefficients are going to be 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. And with those, now we proceed to simplify. All right. 4 to the 4th, that's 264 times 1. Okay, well, that's going to stay 256. Sorry about that. 256. And then your x has the 4th power. Plus 4 to the 3rd power, that's 64. Oh, but times another 4. Oh, well, that's back to 256, isn't it? So that's 256. You have your x to the 3rd. And you have a minus y. Oh, okay, so instead of being a plus, this is now a minus. So that's now minus because of that negative right there. 256 x to the 3rd times y. Okay. Plus, okay, now that's going to be a square, so that negative will go away, so now it is plus. Let's see, 4 squared is 16. 16 times 6, that's 96. So that'll give us plus 96x squared, y squared. Again, the square got rid of that negative, so we don't need to worry about that one anymore. Okay? Plus, oh, but now that's going to be a negative, right? Because negative to a 3rd power will stay negative. That's going to be minus. 4 times 4 is 16. You're going to have your x with just the power of 1, and now your y, the negative has already been thrown to the front, so you're going to have y to the power 3. And finally, the last one, you have a negative to an even power, so that'll be a plus again. And that's just 1 y to the 4th. So in fact, instead of writing 1 y to the 4th, I think I'll just write y to the 4th. And that is the expansion. Instead of taking 4x minus y, multiplying times itself 4 times, and combining coefficients, this gives us a more succinct way of finding that. Okay. Sometimes you don't care about the entirety of the computation. Sometimes you only want just a specific term. So here, let's find the, let's go with the 8th. Let's find the 8th term of x squared plus y to the 3rd raised to the power of 8. You know what? Let's find the 6th term. There we go. Let's keep it closer to the middle. Right. Not that it matters. So let's find the 6th term of the expansion of x squared plus y to the 3rd, all raised to the 8th. All right. So here's a binomial, and you're going to raise it to the 8th. Now, one thing you could do is you could just find all of the expansion and then just count and say 1st, 2nd, 3rd, 4th, 5th, 6th. Oh, there it is. However, if you don't need all of them, why would you find all the rest of them? So let's go ahead and see if we can find just that one term that we're looking for directly. All right, so we know that terms have a specific look. They look like n choose r. You're going to have your first term, x squared, raised to some power. And then you're going to have the second term, y to the 3rd, raised to some other power. Now, specifically, you know that that power on the end always matches this bottom number. Okay, so that's going to be r. Right? So if that's 5, that's 5. That's 9, that's 9. You notice that always happens. This bottom number matches that power there. And you'll also notice that the difference of those two numbers gives you this power. 4 minus 0 is 4. 4 minus 1 is 3. 4 minus 2 is 2. 4 minus 3 is 1. Okay, so these two numbers, if I subtract them, if I take the big one minus the small one, that gives me that power. Okay, well, I already know what n is. N is always the power on my expansion. Here, whatever this number is, that's equal to n. So really, all I need to do is find what r is. Once I know what r is, I can plug them in right here, and I get my result. Okay, well, let's see if we can't find what r is. Okay, here, this is my first term. That's my second, my 3rd, my 4th, and my 5th. Well, notice that in my first term, r is 0. In my second term, r is 1. In my third term, r is 2, 4, 3, 5, 4. Oh, it looks like that number on the bottom, the r, is always 1 less than what term I'm looking at. Right? In the third term, it's 2. Same thing up here. In the 4th term, it's 3. In the 6th term, it's 5. So here, our value of r will be 1 less than what term we're looking for. Since we're looking for the 6th term, since we want term number 6, then r equals to 5. All right, well, there we go. So that means that the term we're looking for is going to be 8 choose 5, 8 choose 5, x to the power 2 to the power, all right, take the difference of those. 8 minus 5 is 3. And then y to the 3rd to the, and then use this bottom power, 5. All right, and there we go. 8 choose 5. Again, if we have our triangle, we can go ahead and go to that. I don't have the 8th row of my triangle. I could find it. Of course, I can always use the formula that, using factorials, that would be what? 8 factorial over 5 factorial times 8 minus 5 factorial. That would work. Or, if my calculator has the ability to do this, I could always do that. All right, so here I have 8 choose 5. So on my calculator, that's that C button. So 8 choose 5. And that's 56. All right, so there we go. That's 56. Here, x to the second to the third. Remember, when you multiply two things, well, whenever you have something that has a power and you raise that to another power, you multiply those two things together. So that's x to the power 6. And here, y to the third to the fifth, you multiply those together, and that gives you y to the power 15. So without having to find all of the other terms, we can directly find a single term if that's what we need. So go ahead and give that a try. Find the third term. Of, let's see, x plus 2y to the power of 6. All right? You can, of course, expand the whole thing out, but that's wasteful, right? You are really looking for just one term, so try to find just that one term. Go ahead and pause the video, give yourself the time you need, and once you're done, go ahead and unpause, and we can go through that together. All right, so we know what it's supposed to look like. It's n choose r times, well, let's see, we want the first term, which is just an x. The power there is going to be the difference of those two numbers, n minus r. And then we're going to take the second term, which is our 2y, and the power of that one is always just the same as this bottom number, this r. So really, we just need to find our n and our r. Okay, well, the n is easy. It's just whatever power we're using. Here, n is equal to 6. We're looking for the third term, which means we're going to use r equals to 2. Since we want term number 3, then we have r is equal to 2. Right? The third term uses r equals to 2. Up here, the fifth term uses r is equal to 4. 1, 2, 3, 4, 5. Oh, r is always one less than the number of terms. So here, we want term number 3, r is equal to 2. Okay, so let's plug those in. That's going to give us 6 choose 2. X to the difference of those two, that's going to be 4. And then 2y to the power of that bottom one, that's 2. All right, well, 6 choose 2. That is one that I had on my triangle before, or you can grab a calculator, or you can use the formula using the factorials. And either way, you're going to get 15. Notice right here, I computed that one earlier with this formula. 6 choose 2 is 15. Or on the 6th row, the second one, that's choose 0, choose 1, choose 2, that's 15. Either way, you get 15. All right, so here, 2 squared is 4, times that 15, that's going to be 60. That's got an x to the power of 4. Here we already used that 2, so now we're just looking at the y, which is going to be raised to the power 2. So that's 2 squared is 4, times 15, that's 60, x to the 4th, y to the 2nd. And that gives us our result. One thing to note is that the use of the binomial expansion theorem will be twofold. One will be, of course, as a nice shortcut for computing multiplications. Here you can expand something without having to go through the full multiplication. It just gives you the result almost immediately. You do have to do a little computation, but it's a lot faster than multiplying something out 4, 5, 6, 7, 8 times. However, the other reason it will be used is in calculus, we are going to be using the binomial expansion theorem to prove something about what is called a derivative. Right? So the use of the binomial expansion theorem is 1, computational, but 2, it's used for proofs of greater, more important theorems later on down the line. Right? So that brings us to the end of this section and the end of this topic. If anybody has any questions, comments, or problems, please make a note of those. Reach out. And I hope everyone has a nice day.